Lastly, before we can talk about the classification of force vectors, we have to introduce the principle of transmissibility. If we assume our body is rigid, that is, it is non-deformable, all we really care is about the external effects an applied load is going to cause onto the body, i.e. the reaction the force or forces elicit. When we talk about a force being applied to the body, say we have a forklift lifting a crate, and this is shown as figure A. The forks of the forklift are lifting the crate from the bottom. And if we assume this is one force lifting at the center, we can draw a line of action. That is what the force lies along and how it interacts with the body. The line of action is a geometric representation of how this force is going to be applied to our body. And it is a line through the point at which the force is applied. That is, it has the same direction as our force. Now, the principle of transmissibility states that our force can be moved along our line of action for a rigid, non-deformable body, and our body will elicit the same response. For instance, in figure A below, we can lift the crate from the bottom and it will have a tendency to move up. Or we could lift the crate from the top along the same line of action and it will still have the same tendency to move up. This makes sense. If you're able to push a car or pull a car along the same line of action, you're going to cause the same tendency for that car to move in the direction of your applied force. When we talk about force systems, we have to define a few. The first is a concurrent force system. And in general, a concurrent vector system is one where the lines of action of all force vectors intersect a single point. So if we look at the diagram below, we have an 80 Newton, a 100 Newton, and a 120 Newton force, all originating from the origin, and our line of actions are intersecting at this single point. Now, non-concurrent force systems are one where the force vectors do not share a common line of action. If we consider the schematic below, we have an 80 Newton force applied to the left of the block, a 60 Newton force applied near the center, and a 75 Newton force applied to the top right. If we drew the line of actions of our force vectors, we would see that they do not intersect at a common point. Now, a parallel force system is where the line of actions of all force vectors never intersect. If we consider a beam that is loaded below, say we have a beam that is spanning a gap, and we have two 60 Newton applied loads that are acting in the negative y direction, we're going to have some reactionary forces existing on the left and right hand side of the beam to support it. Since our reactionary forces are existing in the positive y direction, and our applied loads are existing in the negative y direction, and neither of these forces have any x component, they'll never intersect. That is, the lines of action representing these forces are parallel. Within a parallel force system, we can have distributed forces. And a distributed vector system is one where the forces are not applied at a singular point, but they can be applied rather over a length or area. Now, these force systems provide much more accurate description of what's physically happening within a system. If you consider your car, your tire is not acting as a point force on the road. Rather, as that tire deforms, you're going to spread part of the weight of your car over an area. Now, within our distributed force systems, we can have two subsets. We can have a distributed force in two dimensions, and that is where our force is applied along the length of our member. Our force profile is described in units of force per length. That is, for example, in our schematic below, we have a force of 2.5 kilonewton per meter that is applied over a length of 4 meters. Now, if we multiply that force by the length at which it is applied, we're going to determine the resultant, i.e. there would be a total of 10 kilonewtons acting on that body. However, you have 2.5 kilonewton per meter actually being applied over that length. Lastly, we can have distributed forces existing in 3 dimensions, and those are where our forces are applied over the area of our member. Now, our forces are going to be expressed in units of Newton per meter squared, such when we multiply it by the area it acts over, we're going to have a resultant in newtons. Now, in the previous example, we saw that our distributed load was constant. It doesn't have to be. As we see in this example, we have a higher applied force when z is equal to 0, and that force begins to taper off as z increases. So we can say our force is a function of both our x and z directions. For in the x direction, we have no force from 0 to 1, and then 5 onward, we have no force being applied as well. Last but not least, we can have a situation where we have collinear vectors. And this is where all our force vectors share the same line of action. If we consider the system of bars below, we have 3 40 Newton loads being applied at A, B, and C. Now, although these force vectors all share the same line of action, they are not concurrent. That is, they are not sharing a mutual point of intersection.